Okay, students, now we are going to see the subject transmission lines and RF system. Under that, we are going to solve one of the Smith chart problem. On completion of this, the students will be able to describe what is meant by Smith chart and what are the applications of Smith chart. Example, consider the problem. A 30-meter long lossless transmission line with characteristic impedance is 50 ohm operating at 2 MHz is terminated with the load ZL is equal to 60 plus J40 ohm. The operating voltage is 0.6 into C on the line. Find the reflection coefficient, standing wave ratio and input impedance. Before solving this, first we have to normalize the load impedance. The normalized load impedance is ZL dash equal to ZL by Z0. ZL value is 60 plus J40 divided by 50. So after division, the rectangular form of normalized load impedance ZL dash is equal to 1.2 plus 0.8. So 1.2 is the resistance value, 0.8 is the reactance value. The resistance value is drawn in the horizontal line and it get marked in the horizontal line, and the reactance value is marked in the interior circle of this Smith chart. Here the plus symbol represents the reactance is located above this horizontal line. Here if it is minus means the reactance is located below this horizontal line. Here R value is 1.2, a line is drawn from 1.2 and a line is drawn from 0.8. The meeting point of both the line is the normalized load impedance ZL dash. Then draw a circle by keeping 1 at the horizontal line as the origin and this normalized load impedance as the radius. You draw a circle. So in the circle, the right hand side value represents the standing wave ratio of the transmission line. Next, project a line from the origin of the circle through the normalized load impedance up to the outer circle of the Smith chart. In the outer circle, the length is represented by 0.172 lambda. Next, we are going to find the input impedance. Here, the length of the line is some 30 meter. So, we have to locate the input impedance at 30 meter away from this load impedance. So, find the load distance in terms of lambda. So for that, we are going to find the relation 0.6 into C. C represents the velocity of the light in open space. That is 3 into 10 to the power 8. So 0.6 into 3 into 10 to the power 8 is 1.8 into 10 power 8. So lambda is equal to V by F. Here substitute the V value and the frequency is 2 MHz. So 2 into 10 power 6. Now 90 meter, the lambda value is equal to 90 meter. So the wavelength is given by 90 meter but the length of the line is given by 30 meter. That is equal to lambda by 3. In terms of lambda, its value is lambda by 3. Meter is converted into lambda. Its value is lambda by 3. So this lambda by 3 is equal to 0.33 lambda. So move this length from 0.17 to 0.33 lambda. A line is located here. Its value is the extend this line and this line intersect a point at the unit circle. So this point is the input impedance. It have a real value of 0.48 and its imaginary value is minus a 0.03. That means its value is just below the horizontal line. Okay, so the input impedance is given like this. So the SWR is just the right hand side of the point where the circle cross the horizontal line. That is the standing wave ratio of the given graph. So the total length traveled from this to this input impedance is 0.172 lambda plus 0.33 lambda, that is 0.505 lambda. Some of the quiz question. A Smith chart is based on the polar plot of, this one is a complex concentric circle over which the load impedance is located above the circle. Thank you.